Okay, here we go. Today, I wanted to show you our schedule right here because of what's coming up in the future. So today is the 26th. You can see we're on Module 14A, Life Science and Chemistry. I know we're bringing chemistry back up, y'all.
Yay!
No.
Okay.
Wait, I thought we weren't doing any life science because this was physical science.
Well, and so it says today, Life Science and Chemistry, and I don't know how much life science is in today's presentation. I don't know much of it. And supposedly next time, Life Science and Physics. Don't know. I don't have that presentation yet. I'm not making them. Now look at number 15. Look at Module 15. Notice we do not have a quiz over Module 15 because 15 is different. It's a little bit of a review for the year, and it talks about how we go about doing scientific research. All right, and you're supposed to have a research project. I have no idea what that looks like. I don't know. Okay, here's what I'll do is I will spend this week. I've been completely preoccupied, right, because I took my marine biology class down to the coast, and now it's over, so now I can be thinking about my other classes a little more. So I'll figure out what that is, and next week I'll give you a little more instruction on what I'm expecting, because look at this day right here. Research project presentations. Remember how you had a project just before Christmas? We're going to have a project like that again, but it's going to be a research project. And like I said, I'm not exactly sure what that looks like. And then notice on our last day we do have a final exam in this class. Okay, and it should be very similar to the midterm in that it's going to be mostly multiple choice. All right? So that's what we have to look forward to, and then we're on summer break, right? And we're done with physical science. Hooray! Yeah. Typically after 8th grade, 9th grade is Biology 1. That should be the next course that you should be taking. Are you in 9th grade?
I'll be in 9th grade next year.
Yeah, okay, so you got to get biology in there at some point. So typically the colleges like to see Biology 1 in 9th grade, Chemistry in 10th grade, Biology 2 in 11th grade, Physics in 10th and 12th grade.
Instead of doing chemistry, can you avoid chemistry somehow?
You cannot avoid chemistry.
By doing marine biology?
No.
Can you avoid
Can't do that.
physics too?
Yes.
Biology.
You can avoid biology too. Yeah, you can take chemistry 2 instead, although nobody teaches it
I'm
here.
in 10th grade next year, so I'm not going to have enough time to do all the science.
Oh yeah, okay.
You're in 9th grade?
Yeah.
Yeah, so that's just typically that's what the colleges like to see on the transcript.
I was told this was the 9th grade class.
No.
Apparently not.
It's 8th grade. All right, so here we go. Module 14A, Chemistry and Physics in the Sciences. Yay. We're going to really be looking at organic chemistry, which was one of the most difficult courses I ever took in college, organic chemistry. Although the labs were great. The labs for this won't be great because we can't do all the fancy organic chemistry stuff because it's dangerous and it requires very, very expensive glassware. All right, here we go. Here's our first set of blanks right here. Organic chemistry is the study of carbon compounds. Carbon compounds. Organic compounds contain carbon and other elements. Mostly carbons, hydrogens, oxygens. We call those hydrocarbons. And we're going to see 3 forms of carbon. You're going to write down on the little chart thing right there. The 3 forms of carbon we'll look at are diamond, graphite, and something called fullerene, which are pretty cool things. All right, so we've heard a lot about things that are organic, right? You go to the grocery store, your vegetables are organic, your fruit is organic, that kind of thing. It's a little different here. Do fruits and vegetables have carbon in them? Yes, they do. So in that regard, it is organic. But what they're talking about is the stuff they put on them while they're growing. You know, insecticides and things like that. That's what the organic means for that. Here, organic's going to be referring to what is it made of? Is it made of chains of carbon? That's organic chemistry. All right? Okay, so let's take a look at these 3 things. We got that written down? Diamond, graphite, fullerene. So here we're looking at diamond, and it has a shape like this. And here we have graphite, which is in your pencils right now. You know, we used to say lead pencils. It's not lead, it's graphite, which is a very soft form of carbon, which is really interesting. So see how it's shaped right here? It looks like little sheets over here on the right. It turns out that diamond is the hardest thing we know. The hardest thing we know. And graphite, which is made of the same stuff, is one of the softest things. That's why it stays on your paper when you rub your pencil. It's so soft, it comes off onto your paper. Yes?
So you would not get lead poisoning from this?
No, you don't get lead poisoning from your pencil because it's not lead. Lead is also soft. Maybe at some point they did use lead, I'm not exactly sure. All right, what's the third thing? We have diamond, we have graphite, and we have what? What was the third one?
Fullerene.
Fullerene, there it is. These are really cool because every black dot you see there is a carbon. So they're all put together and they form this kind of geodesic dome, this kind of cool formation. We call this a buckyball. And you're going to see why here in just a minute, why it's called a buckyball. It's actually honoring somebody, a man
Can you
named...
buy those at Buc-ee's?
You have to ask him, I guess. Yeah. It's named after a guy whose name was Buckminster. His name was Buckminster Fuller. That was his name. Fullerene comes from that, from Fuller. And buckyball comes from his first name. So let's watch a little video on it.
Allotropes of carbon. The element carbon occurs in different forms in nature with widely varying physical properties. Both diamond and graphite are formed by carbon atoms. The difference lies in the manner in which the carbon atoms are bonded to one another. In diamond, each carbon atom is bonded to 4 other carbon atoms, forming a rigid 3-dimensional structure. In graphite, each carbon atom is bonded to 3 other carbon atoms in the same plane, giving hexagonal arrays. One of these bonds is a double bond, and thus the valency of carbon is satisfied. Graphite structure is formed by the hexagonal arrays being placed in layers, one above the other. These 2 different structures result in diamond and graphite having very different physical properties, even though their chemical properties are the same. Diamond is the hardest substance known, while graphite is smooth and slippery. Graphite is also a good conductor of electricity, unlike other nonmetals. Diamonds can be synthesized by subjecting pure carbon to very high pressure and temperature. These synthetic diamonds are small, but otherwise indistinguishable from natural diamonds. Fullerenes form another class of carbon allotropes. The first one to be identified was C60, which has carbon atoms arranged in the shape of a football. Since this looked like a geodesic dome designed by the U.S. architect Buckminster Fuller, the molecule was named fullerene.
Okay, yeah. After Buckminster Fuller. So when they said it was like a football, they meant a European football. In other words, a soccer ball. We call them
What's
soccer
in a
balls.
hexagon shape?
But you know how the soccer ball has those little faces on it? Yes.
So what exactly is fullerene in? Like,
I do not know. I don't know much about fullerene, to be honest with you. So, good question though. But here, properties of diamonds. I'll look into it. In fact, I just got an idea for a really cool lab when I was watching that video, and we'll do that next week. It's a way of using graphite as a conductor of electricity. Yeah, so that's pretty cool. All right, let's talk about the properties of diamond. Here we go. A very high melting point, almost 4,000 degrees C. Wow. Very strong carbon-to-carbon covalent bonds have to be broken throughout the structure before melting occurs. So they don't melt very easily. All right. Very hard. It's one of the hardest things we know. This is due to the need to break very strong covalent bonds in 3 dimensions. And furthermore, in order to cut a diamond, you can only cut a diamond with another diamond. That's the only way to cut a diamond. And so jewelers who take a rough diamond and cut these little cool things, these little facets onto it, use another diamond to do that. They might use a blade like a saw blade, but the saw blade has to have diamond on the end of the saw blade or else it won't cut it. Yeah, that's how hard it is. It does not conduct electricity. Diamond does not. All the electrons are held tightly between the atoms and they are not free to move and have electricity pass through them. It's insoluble in water. That's good. It doesn't melt, right? It doesn't dissolve. Also in organic solvents. It doesn't dissolve in anything. There are no possible attractions which could occur between solvent molecules and carbon atoms to outweigh the attractions between them. Okay, that's what causes something to dissolve in something, is if something's pulling those apart because they're attracted to them. So carbon doesn't do that. So it's going to stay a solid. And of course they are natural, found in nature, right? We find them, those are the most beautiful ones, although they may have flaws. There is a way to make them artificially. We can make diamonds artificially. In fact, we can make flawless diamonds artificially. You have to start with a little bit of diamond to begin with.
Are they still worth a lot?
if someone doesn't know it's artificial, yes, they're still worth.
Is that illegal?
No, but you're supposed to disclose it. You're supposed to tell people that they're artificial. They're still beautiful, very pretty. Okay, let's watch. This is about diamonds. This will tell us a little more about it.
If you thought the sparkle on your finger was the only diamond in your life, then think again, because industrial diamonds are in use all around us. Even the tiles in your toilet were probably cut with a diamond blade. Top quality, naturally occurring diamonds cost thousands of pounds, but this entire dish of synthetically grown diamonds costs around £50. In fact, the majority of diamonds used in industry are grown synthetically. Man-made diamonds were first created in the early 1950s using high temperatures and high pressure, and the basic ingredient, carbon. In fact, given the right conditions, you can make diamond out of any type of carbon, including burnt toast.
Burnt toast.
Once the bread is truly burnt, it's ground down and squeezed into a mould. Then, a special machine takes it to a pressure 60,000 times greater than our atmosphere, at which point the carbon naturally becomes diamond. And what about the results? Well, your other half won't be too impressed if you propose with one, because 2 bits of burnt toast won't produce a diamond that's visible to the human eye, but you can see them in this photograph with a 10,000 times magnification. Many diamonds are made this way to be used as abrasives. Saw blades and drill bits are coated with them. Several face exfoliants contain diamond, and some eye surgeons use diamond knives. It's in so many things because it's very, very hard. Hardness is measured on what's called the Mohs scale. At the bottom of the scale we have soft things like talc, midway along materials like steel, but at the top of the scale, the hardest naturally occurring thing known to mankind, diamond. Different types of diamonds are being developed which could see us using them in a whole new way. They're made with low pressure. Methane and hydrogen are taken to just 1/100th of the pressure of our atmosphere and heated until they're as hot as the surface of the sun. This smashes the molecules apart and eventually produces diamonds. The results are tiny crystals which can be formed into some of the most amazing shapes, long, thin wires, and large flat plates that can be highly polished until they're see-through like glass. This disc of synthetic diamond is perfectly transparent and so tough that one spacecraft which travelled to Venus had windows made of it. We've got some ice here and we're going to demonstrate one of the lesser known but very remarkable properties of diamond. Chris, how does it work?
Well, basically diamond has an incredibly high thermal conductivity. It's 5 times higher than copper. So what I want you to do is hold that piece of diamond and hold a copper coin in
Yes.
that, and then connect them together onto an ice cube and just tell me which one gets cold quickest.
Within seconds, the heat from my hand alone quickly transmits into the diamond disc and cuts the ice like butter. The amazing thing is, the diamond edge is in fact blunt. That's amazing. That really is amazing. Diamond can also be doped with the element boron to conduct electricity. The fact it can do this, and that it can dissipate heat quickly, means it's likely to be used in electrical devices in the future to give us fast speeds with small chips, giving it yet another use in our lives.
All right, there you go. They're all around us, yeah?
Just gonna run out of diamond though.
What now?
Just gonna run out of diamond.
Well, but we can make diamond out of anything that has carbon in it. So, but very small. They're very small. The you can make a diamond big enough for a ring synthetically, but they don't make them much larger. Okay, what about graphite? Remember, it's made from the same stuff. Grayish black, opaque substance, lighter than diamond, smooth and slippery to the touch. It leaves a mark on your paper, right? And here, a good conductor of electricity due to the presence of free electrons. It conducts heat. All right, so yeah, I'm just thinking of a little lab I have that uses it for like making heat. So it's pretty cool. I'll see if I can get that worked out for next week. How are diamond and graphite different? It has to do with the way they're arranged, the way the atoms are arranged. Graphite has a layered structure. They showed that in the video, consisting of rings of 6 carbon atoms arranged in widely spaced horizontal sheets, whereas let's see, graphite crystallizes in the hexagonal system, but diamond crystallizes in the octahedral or tetrahedral structure. Okay, giving it that big change there, that big difference.
Oh,
Y'all not filling any blanks at all in this?
I thought they were shaped in like a 3D like for graphite. You showed that before.
For graphite, they're in the sheets, like layered on top of each other, like that one. Just ignore those dots in between here, the dotted lines. All right, so what is fullerene? Here we get to fullerene. Fullerene is any molecule composed entirely of carbon in the form of a hollow sphere, an ellipsoid, or a tube even. Okay, and apparently they're happening, naturally. Spherical fullerenes are also called buckyballs. They resemble a soccer ball. Cylindrical ones are called nanotubes or buckytubes, also named after Buckminster Fuller. And I'll look into those and see what we use them for practicality. What are they used for? Okay, what is hydrocarbon? Here we go. We have another blank to fill in here. Hydrocarbons contain carbon and hydrogen. All right, so if we have a chain, what's really cool about carbon is carbon has 4 binding spots. Okay, so I have my carbon and I have 4 places to bond. All right, so what it can do is one of those can be bonded to itself. So I can end up making a large chain of carbons. Okay, and if I have nothing but hydrogens hanging off of them, that's called a hydrocarbon. Now, who remembers what C6H12O6 is?
Sugar.
Say it again?
Sugar.
It is sugar. Did somebody say glucose?
Yeah.
All right, so we have 1, 2, 3, 4, 5, 6 carbon chain like that, and then we have hydrogens and then some 6 oxygens hanging off of it. It can be in different forms. In fact, C6H12O6 also refers to something called fructose. So glucose, fructose. If you tasted glucose, it wouldn't taste very sweet, but if you tasted fructose, you would say that's really sweet. It's also C6H12O6, but it's arranged differently, and therefore it has different properties. Pretty cool. Sort of like the graphite and the diamond. All right, if those bonds between here are all used up, so let's put the rest of our H's on here. And every bond is full. So that means carbon is bonded in 4 spots on every single carbon. That's called a saturated molecule, okay? So saturated hydrocarbons, single bonds in the compound with a maximum number of hydrogens. So what I just drew right there, 1, 2, 3, 4, 5, 6 carbons. So that's C6H8. Yeah. So there's a bunch of what they call those infographics in your book, okay, showing different arrangement of carbon atoms. So they can either be in straight chain molecules, that goes in one of your boxes, straight chain molecules, like I drew right here on the board, or branched chain molecules, or they can form a ring. All right, so if I have a carbon, here I have 1, 2, 3, 4, 5 carbons in a, like a pentagram, right, kind of thing, right, a pentagon. If I just drew it like this, like that, you would have to remember that at every little juncture, every little corner is assumed to be a carbon there. Okay, so that's why how we usually, instead of drawing all the carbons around a C, the letter C around it, we just draw a picture like that to not use as much space. All right, so a straight chain, a branch chain, or a ring structure. That is also known as an aromatic structure when it's in a ring.
The one without the H's around it, a straight chain?
That's a straight chain right there. Yeah. So branch chain, you'll see, I think I'll give you an example of it. If, for instance, if I took one of this carbons and I moved it, so we put the H here, and then I put the carbon up there with the 3 H's hanging off of it. Okay, that's branched. That's a branch chain. All right, and that's going to be part of our lab today, by the way. Okay, so here we go. We're looking at something called butane. Okay, butane has 4 carbons in it. So take a look at the carbons. There we can see a straight chain of carbons, 1, 2, 3, 4. Here we can see a branch chain, 1, 2, 3, 4. And here we can see a ring because it's in a square. See, it's in a square right there? Okay, so what we're looking at is C6H10. And they're all C6H10, but they're different shapes here, right? So we have our structural formula down here. If you made it out of little models down here at the bottom, you can see how different they look. but they're all C6H10. They're all the same formula. They may have different properties based on how they're shaped. Just like I told you about the glucose versus the fructose, the difference in the taste of those. All right, so that is also here. Modeling isomers. Okay, so when we get to lab time, we're going to do something like this, but I think I'm going to use these guys instead of these guys because these guys are easier to do, okay? So, and I'll bring this picture back at the end for us to take a look at it. All right, but this is just showing C6H14. Here we are in straight chain. Here's a branched chain. Here's another branched chain, but different. See my CH3 hanging off of here? I could have had that carbon, and then I could have shown my 3 H's coming off of it, like that, right? But every carbon has to have 4 bonding sides to it. So as long as it's got 4, here this carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4. Then carbon is satisfied.
Are you writing that out on this big link?
Say again?
Are you writing that out on this big link? Big link.
What does it say at the top of your big box?
Draw modeling the solvers activities.
Okay, you know what? We're going to wait till we get to lab time to do that, okay?
Okay.
Yeah. All right, but here I'm just showing you how each one of these is different. Notice I have 2 CH3s hanging off the side on this one. But meanwhile, they're all C6H14. So these are called isomers. So an isomer just means it's a different shape of a molecule. It's got the same number of elements in it, but it's a different shape. In the video we watched, they called it something else. What did they call it? They didn't call them isomers, they called them allotropes. So allotrope is another word. It's just a synonym for that. Okay, so here's some isomers of hexane. That's 5 carbons. Notice here in my linear one right here, notice we just left the H's off. Okay, we're just going to assume you know the H's are there. It just makes it a little neater to look at, right? So notice here I've got it straight line. Here's a branched chain on the 2nd carbon. Here's a branched chain on the 3rd carbon. Here is a branched chain with the 2 hanging off. Here, alternating like this. Notice their names. So this is called hexane or N-hexane. N kind of sort of stands for normal, but not necessarily for sure. We have 2 methylpentane, 3 methylpentane because it's on 2 here, it's on 3 there. Here we have 2 dimethyl butane and 2,3,2,3 dimethylbutane. All right, that's how the chemists, and this is organic chemistry, like I said, okay? So, yeah, it gets super complicated. Yes?
Is organic chemistry just carbon?
Yes, all just carbon. And you might think, well, it's just about living things. No, not necessarily. There are things that, for instance, things like alcohol. You know, like rubbing alcohol might just be a hydrocarbon version, okay? Things like methane, butane, things like that aren't necessarily from living things, may have originally come from living things, possibly in a fossil type situation. All right, now, if we don't have every single carbon surrounded by a single bond, then we might have a double bond somewhere. We call that unsaturated. You've probably heard of that when it comes to oils and fats, right? A saturated, polyunsaturated fat or a saturated fat, this kind of stuff. And the nutritionists keep changing their mind about what's good for us and what's bad for us, right? It just has to do, is there a double bond? That's all it means, is there a double bond in there? Okay, so here we go. An unsaturated hydrocarbon has a double or triple bond between the carbons and hydrogens somewhere along the chain. They do not have the maximum number of hydrogen atoms because there's a double bond that satisfies carbon. There's not room for an extra hydrogen. So therefore it leaves that off, okay? So here's our question. The 3 types of unsaturated hydrocarbons are alkenes. Alkenes. And you might want to run underneath it, they have double bonds. Alkenes have double bonds. When I was in college and I took my organic chemistry, I always was confused between alkenes and the next one, the one at the end, alkynes. And if someone just told me, look for double bonds, I think I would have been happy there. Aromatic hydrocarbons, what are those? Remember I told you what aromatic meant? Those are the ones in a ring, okay? Those are ones that are forming a ring structure. And they have, but the ring structure has a double bond somewhere in it. And then our alkynes. They have triple bonds, okay? So we have alkene is double, alkyne is triple. Aromatic is a circle.
They're both alkynes?
Alkene, alkyne. They're both unsaturated. The alkene has double bonds, the alkynes has triple bonds, the aromatic has a ring structure with a double bond in it somewhere. But honestly, I don't even teach this to my chemistry students. So the fact that we're learning it in physical, I don't get it, but it's okay. I mean, I didn't write the book.
So it's useless.
It's not useless, it's very useful. It's just maybe above 8th grade level is all I'm saying. I don't know.
So useless right now.
Well, okay, maybe right now, but you need to know it for next week on the quiz, or 2 weeks on the quiz, right? Okay, check for understanding. Here we're just gonna go through just a little review here. 3 forms of carbon are diamond, graphite, and fullerenes. That sounds like a good quiz question right there, right? 3 structures of hydrocarbons are straight, yeah. Straight chain, branch chain, and ring.
Oh, you were asking. I didn't know you were asking.
Oh yeah. Sorry, I think these are maybe the OIOs. 14.1 to 14.2 OIO on your own. An isomer is any molecule with the same molecular formula but a different structure, and I think we're asking if that's true or false. Same molecular but a different structure. That's true.
I got it.
That I don't know. I didn't put the answer in there. Oh, I guess it's not asking for true or false. It's just telling us that. And then 14.4, a triple bond is found in an alkyne, true or false? True. Alkene has a double, alkyne has a triple. Sounds like a good quiz question again, okay? All right, here we go. Hydrocarbons as fuel. Fossil fuels are mixtures of hydrocarbons formed from the remains of plants or animals, we think. We're pretty sure. We call them fossil fuels because they came from fossils, we think. They're full of carbon, we know that. And carbon is what life is made of, so it makes sense that they came from plants or animals. All right, so we have 3 types of fossil fuels. Here we go. Number 1, coal. We think that's compressed plants.
That's really
Very coal. Yeah, thank you.
Dude.
Next we have natural gas. Natural gas. And the last one would be petroleum, otherwise known as oil. Okay, so the oil like we use for our cars, things like that. Now, in order for these to burn, we see some burning over here on this little picture. It's called combustion. Combustion of fossil fuels requires oxygen. Did we study that already about combustion?
Yeah.
Yeah.
What did we do for our lab when we studied that?
I don't think you do.
I think we lit something on fire.
Did
Yeah,
we?
we
And then we put we lit
Oh, we did
something
the
we
egg
lit a
thing.
candle and then we put a cup over it, I think.
Oh, and we put the egg in the
Yeah.
bottle? Is that
Yeah,
what we
and
did?
then it
But
squeezed-
I
it, like,
thought that was
squeezed
air
in there.
pressure.
It was hard. It was hard to warm.
I thought that was air pressure.
Maybe.
Oh no, you have 9 OIOs.
Okay, I'm going to show you the chemical formula for combustion here. All right, complete combustion requires oxygen and it produces carbon dioxide. You can just write CO2 right there. And write the complete combustion of propane, which is C3H8. This is it right here. C3H8 plus 5O2 yields 3CO2 plus 4H2O. Those big numbers in the front, those are called the stoichiometric coefficients. And they have to be there in order for the thing to balance. Okay, I have to have whatever I have on this side, I must also have on this side. So I had 3 carbons over here. That's why that big 3 went in the front of the CO2. Remember that from our time, our really fun time of studying chemistry.
We have like
Yes.
a bunch of those like little cans sitting around in our phonics. I don't know why.
Little cans of, this?
Yeah, just a bunch of random
Are they
ones.
full of propane?
No,
Oh,
they're just empty.
really?
And I asked my dad, I said, why do we have all these in case we need to get propane? And I said, okay.
Okay, yeah. Yeah, you might want to get them filled with propane. And then you'll have it
There's
available
like
for
maybe
use.
like 5 of them in there.
Okay. Well, I have it for my grill, you know. You may have a propane grill that you use that in.
How
Um,
do the
Wait
O's
for it.
balance?
Okay, so what I have here is I have 3 times 2 plus 4. That makes
Oh.
10. 5 times 2 makes 10.
I don't have to be an O2 for balance.
No, just any oxygens. Good question. Good question. Yeah, so I've got 4 oxygens here. I've got 3 times 2 oxygens there. So 6 plus 4 is 10. 5 times 2 is 10. Yeah. So that is balanced right there, and that's more complex than our photosynthesis. Yeah. Okay, let's learn a little bit about combustion.
combustion. Humans do a lot of burning. In the past, we burned a lot of wood,
Have you seen this
and we
video?
still burn some.
No, I don't think so.
We burn huge amounts of the fossil fuels, coal, oil, and natural gas. Sometimes we burn hydrogen. Although we burn different things, in every case, the substance that we burn, the fuel, combines with oxygen in a chemical reaction that releases energy, usually heat and light, and often sound. Reactions of this type are called combustion reactions. Energy isn't the only product of combustion reactions, but usually the other products are treated as waste. For example, when we burn coal, it produces carbon dioxide as well as energy. And when we burn hydrogen, we get water as well as energy. In both of these cases, the chemical products are gases that we leave to drift off into the atmosphere. Some combustion reactions are very fast. If you mix hydrogen and oxygen gases before setting them alight, the reaction occurs in a split second. We call it an explosion rather than burning. And it's the same inside a car engine. The fuel is mixed with air in the cylinder and explodes with a spark from the spark plug. But put the same fuel in, say, a camping stove, and it burns. It's the same combustion reaction, just happening at a different rate. Combustion reactions are incredibly important for the way we live. We use them to keep warm, to heat water, to cook, to move cars, ships and planes, for manufacturing and to produce electricity. But they're not always helpful, and they can get out of control.
California.
Oh, I shouldn't laugh, I guess. Not funny. Okay, there we go. There's our combustion. Incomplete combustion. Okay, when there's not enough oxygen, we can have something called incomplete combustion take place. Okay, it's running out of oxygen essentially is what's going on there. It's dangerous because instead of making CO2, it makes CO, which is carbon monoxide. Carbon monoxide is deadly poisonous to human beings.
Why is that?
It fills in the place where oxygen should go, and it doesn't allow the oxygen to bind to the molecules. All right, so carbon monoxide is a poisonous gas. So when you write the incomplete combustion equation of propane right here, we can see that we end up making carbon monoxide. Sometimes, look, here when we have just enough oxygen, we're making CO2 at the top one here, but we're also making carbon monoxide.
Both.
And then down here, we're only making carbon monoxide because it gets to that point where it just has run out of oxygen. Now, do y'all have fireplace at your home?
Yes.
A gas one.
Oh, it's gas? Okay. If you burn, my
I
fireplace
use
burns
wood.
wood.
I
Okay.
usually do.
So
Yeah,
when you burn the wood in there, of course, the fire's going, it produces the heat and all that kind of stuff, you know, and the light, and we see all of that. And then after a while, you may notice that it's drawing oxygen towards it. That's why it draws it up the chimney, by the way, which is useful to keep the smoke from coming into your house, because it's drawing in the oxygen that's around it. But when it starts really roaring and really going, it starts to have incomplete combustion. And so therefore, fortunately though, it's being drawn up your chimney. It doesn't usually bother you. It's not going to cause a gas to build up into your house. But eventually what happens is I have so little oxygen I can't even make CO, which is carbon monoxide. All I can make is C, which is carbon. And you know what it looks like on the back of your fireplace? Soot. You ever seen that black soot back there? That's just the carbon from incomplete combustion going on back
So
there.
incomplete combustion always happens. Right?
It typically does because the fire gets hot enough. Yeah, it happens in our cars. And that's why cars, out of the exhaust, they're exuding from the exhaust carbon monoxide. That's why you never want to be in a closed, guys, you never want to be in a closed garage while your car is running. People were trying to get warm last year when we had the big freeze. People went in their garage, turned on their heater in their car, and they're sitting in their car, but they had the garage door closed. Well, carbon monoxide's building inside the garage, and if you're not careful, you'll fall asleep and never wake up. Okay, it's deadly. The deal is, on our cars now, we have, by law, required that they turn most of their carbon monoxide back into carbon dioxide, and they do that with a process called the catalytic converter in your car. and it uses a metal to pull the things back together and turn CO into CO2. Yes.
So with my dad's fancy new
He probably doesn't have a
not
catalytic
new,
converter on
but
that one.
old
Yeah.
car,
If there is
it it actually set off the carbon monoxide alarm.
I'm not surprised. Where was the carbon monoxide alarm?
It was in the garage, but it was just a small pocket of that carbon monoxide went out and made its way to the sensor. So
Okay.
we had the fire department come. And,
Wow.
Yeah.
Yeah, so a car that's older doesn't even have a catalytic converter on it. So that means it's only making carbon monoxide. Well, not only, but a large amount. So cars, even with catalytic converters on them, my car that I just had to get rid of because it was giving me so much trouble, had 3 catalytic converters on it, and 2 of them were clogged. So it was probably producing a lot more carbon monoxide. Question?
There was a guy at TIG, and he was like warming up his tank with a little heater, and just like carbon monoxide in his tank.
Yeah, it happens in like small campers and things like that. That's why if you're going camping, maybe go with an electric heater. Electric heater doesn't do combustion the same way; it just heats up an element.
Does it say H6?
Because there's no way to stop it.
Say again.
There's no way to like stop it from being.
Add more oxygen. So, okay, good question. So, Erebus is saying, well, there's no way to stop the incomplete combustion, right? Well, let's say we're in that little camper, right, and we have our flame going or whatever. Oh, crack the window open. Guess what? It'll pull more oxygen in, and it'll allow it to go back to complete combustion. I just got to get enough oxygen into it. Have you ever noticed when you try to start a fire and they use those thing called the bellows to get it started? Because we're pushing oxygen on it. You might think blowing on a candle blows it out. Well, actually, it gives it life unless there's too much force to it, then it blows it out, like your birthday candles, right? All right, so bring on the oxygen gas. When combustion is occurring, there must be plenty of what gas? Oxygen. If there's not enough oxygen, what dangerous gases form? Carbon monoxide. So I found this interesting. We're gonna light some candles here in a minute and take a look at our flame. Okay, and it says here that at the wick, of course, the fuel of our candle is wax, and that wax is typically made from, let's say we were using beeswax, it came from a bee, right? We're not, we're using synthetic wax. We're going to see here that right here there's something called the wax deficient region, and we start burning the wick itself. That's why the wick turns black, because it's burning. Oxygen deficient region, it looks kind of orange. What does this say? Unburned carbon particles along the sides here. The hottest part of the flame is where complete combustion is taking place, and then cooled carbon at the top. So we'll see when we're looking at it closely, but not too closely so your face and hair don't get too close to the flame, please, because I, for some reason, forgot my other bucket at home, and guess what's in the other bucket? Goggles. Yeah, so we gotta be really careful today, y'all.
I have glasses, so.
All right, if carbon monoxide is being produced, we do have, David just brought it, oh, here's oxygen, here's carbon monoxide. David just brought up a carbon monoxide sensor. Most houses have a CO sensor to tell you if you have carbon monoxide forming. Also, I will tell you carbon monoxide is heavier than air, so it'd be good to have your carbon monoxide sensor not high up but lower down on the wall. Yes?
One time I was making pancakes and I burnt my hair, and so I went to it was like bad, and so I went to the shower to like, and then I forgot to turn it was a gas stove, and like we had our little alarm thing go off.
Oh, sure, because of the smoke that was made. And then you probably noticed the bad smell.
Oh, my hair smells terrible.
Yeah, we have sulfur in our hair, and when you burn sulfur, it makes a stinky smell. Yeah.
So carbon monoxide, when you carbon use it, it gets into the air. Can it turn back into carbon dioxide in the air?
Once it's in the air, no. Not unless it goes. So the way we do it is put it through this piece of metal in a catalytic converter, which pulls it closer together. So unless you have some sort of chemical reaction to do it, the answer is no.
Because if there's carbon monoxide in the air, it can't turn back into carbon dioxide. What happens to it?
It's going to drift off just like a regular gas. We have carbon monoxide all over the place. We're making it all over the place. But when I say it drifts, it kind of drifts out this way because it's kind of heavy. Kind of drifts out like that. Yes?
Carbon monoxide is also that gas that will explode if you have a large amount of it.
No.
And you
Hydrogen explodes.
Oh.
Yeah. Oxygen allows explosions to take place because it allows the combustion to go. All right, because didn't we talk about our atmosphere having 20% oxygen in it? And if it had more, we'd have spontaneous combustion of things. Right, because oxygen, while it's not combustible itself, it allows combustion to take place. It's a chemical reaction, yeah.
Then how come carbon monoxide wasn't listed when you're learning about our atmosphere?
It's just not big enough. It's in that little thing called other gases. In the gigantic atmosphere, it's just not measurable, but it's there.
If all of our cars emit it, we're
Yeah,
in
it's
everything.
here for sure. Remember, plants can, well, they like to use CO2, of course, but here we go. Complete combustion, I've got my hydrocarbons, fuel, I've got my oxygen, I'm making CO2, and I'm making water. Okay, here when I have incomplete, it's really when the fire gets roaring really fast, it can't pull the oxygen in fast enough, so I am still making CO2 unless it gets really, really vigorous, and then I have that CO right there. And then here you can see when it gets really fast, when I have no oxygen, it's just carbon, and that leaves that soot behind. Okay, so that's how combustion works. Are we good? All right, it's time for lab. We're gonna build something. We're gonna do our combustion part first and get that out of the way, and then we're gonna build these isomers out of marshmallows.
Ooh.
Stuff they use for like.
All right, so I'm gonna bring that back up, and we're gonna do our combustion first. Okay, so this is what I think we're gonna build based on those.
No, we
Can I
can do
go
that
early?
So,
Do you need to go
burn my
early?
hair off and then I'll go
No,
bald.
you would probably
That's
die.
the answer.
Miss Cass,
Yes.
one more question. In a
You'll
fire,
probably die or be
If-
severely injured.
it's
eventually.
burning too fast.
Uh-huh.
I couldn't get in the oxygen, but you're making
Probably die. 'Cause
carbon
I-
monoxide. Can you put in more oxygen?
Yes.
Nah, shit.
If you add more oxygen.